So hello guys, welcome to Examinalist Quantum Mechanics lecture series. So as in our last lecture, we discussed that we will derive the complete uncertainty principle. So this is the exact uncertainty principle just by using this already known things. Okay. Now, what I want to say you is that the basic definition of the momentum vector, the momentum operator. Okay, so what is the definition of momentum operator? The momentum operator is defined as minus I, okay, h cross del by del x. Okay, this is the momentum operator. And what is the position operator? So the position operator is just defined by this. So we already know what momentum and position operator do. What I want to say here is that the Heisenberg uncertainty principle is already inbuilt in the position and the momentum operator. It's already inbuilt. Since it is already inbuilt, hence I can claim the fact that just by using these simple definitions, I can calculate this uncertainty principle. Agreed? So let us see how to do that. So before starting, let me tell you something about a very interesting equality called a Swatch equality. Okay. So Swatch inequality states that, so consider you have two functions, two complex functions. One is f, okay, and another function is g. Okay. Then there is a basic definition. The basic definition says that the mod of, okay, so integration of the conjugate of the f function. As I said, f is a complex function, so we can have its conjugate, okay, into g dx. So this is an integral between the conjugate of f and g, and remember f and g are functions of x. Okay, so this is a particular integration, that is just a number, is always less than equals to, okay, so integration of, so if you take the only function, okay, its conjugate and f dx, okay, so this will fetch you a number, and say another integration, so multiplied with, so these two functions are multiplied, okay, so multiplied with g is also a complex function, so conjugate of g into g dx. Okay, so this is the famous Swatch inequality. Now let me just give you an idea before actually deriving the Schwarz inequality in the next lecture. I'll just give you an idea. So so consider this is one, so this is second, and this is a third part. Okay, so there are two symbols here. Either one is less than the multiplication of 2 and 3, or 1 can be equals to the multiplication of 2 and 3. Okay, now the second part is easy to explain. So for example, consider going to give you a very bad example, but I have to do it at this point. It's a very bad example. Okay, so consider you have a multiplication of two numbers, 10 and 9. Okay, then you can see that um, yeah, I left a square, so you have a square here. Okay, so what you need to do is that if you square them, then I can claim that 10 into 9 square is equals to 10 into 10. Okay, so it is like f dot f and 9 into 9. Okay, so after all, this integration will give you a number. Please understand that this integration will, at the end of the day, will give you a number. So whenever you are doing an integration, what do you get at the end? You get a number. Okay, so this is, so second part is equal to this. However, sometimes what happens is that when you do the integration, say consider you get a number 15 after doing the integration. Okay, and then what happens is on the other side, when you do the first integration, say you got a number, say 8, and after doing the second integration, say you got a number 2, then of course 8 cross 2, so is 16, so 15. So yeah, so the first part is satisfied here. So it is a fundamental truth with complex functions. So if you take the mod square of two different complex function inside an integration, then it is always less than the integration which contains the square of first function and square of second function. So this is the famous inequality that we will use in our derivation all along. Agreed? So let us keep this on one side. Okay, so now what we'll do is, for some reason, okay, I'll state the reason. Just for some reason, um, just consider this integral. So what integral? So for some reason you just consider this integral I. So consider this integral. Now why are we considering this integral? Because somewhere at the end of the day you will get this thing. So from here, after doing some 3 to 4 mathematical steps here, okay, you'll get a particular result. The result will be that, so you'll have this type of thing. So I, yeah, let me write it down. Okay, okay, so you'll get something like this. How we'll get to this, I'll tell you at the end. But can you find me the f and the g? Okay, so oh, there is an integration. uh, yeah, so can you find me the f? Okay, so say this is my g. Okay, and say this part is my f. Okay, so by Swatch inequality, what will be my first term? So my first term will look like integration. Okay, so I h cross. Okay, so let me write, so the first term is g star. So so what will be, oh, so first term is say g. Agreed? Oh, sorry, the first term is f. So let me write f. So what is my f? I h cross d psi star divided by dx. So this is my f, and then I'll have f star, I mean f conjugate. So what will be my f conjugate? So you know, conjugate means just convert I to minus I and conjugate of any other function. So what will be the conjugate of psi star? You know, you'll get psi. So this becomes my first term, okay, of Schwarz inequality relation. And then how about the second part, that is the g? So g will be, first consider the g which is xi, and then you have to consider the g star which is x psi star. Okay, and then dx. Agreed? So why do we want to do this? Why is the reason we want to do this? The reason is, if you have a clever look at the terms, then you'll see that the red term is nothing but expectation value of p square. Okay, so if you look at the terms on the right hand side, the first one is expectation value of p square, and the second one is expectation value of x square. Agreed? So then there will be a greater than symbol, and there will be this term. Okay, so let me just put this term, and then there will be this term. Agreed? Now you'd say, why, what are we doing? The reason we did this is that, so remember what is your uncertainty in p? The uncertainty in p was root over of, okay, so let's do like this. So uncertainty in p square is is expectation value of p square minus square of expectation value of p. Okay, now if somehow this term is 0, then you have uncertainty in your p is equals to root over of, okay, the expectation value of p square. Agreed? Similarly, for the x, what you need to do, you know that uncertainty in your x, okay, is given by the expectation value of x square minus square of expectation value of x. If somehow the second term goes to 0, then what do we get? You'll get the uncertainty in x is equals to root over of the expectation value of x square. Okay, now you would ask a question, how the hell can you make expectation value of x and expectation value of p go to 0? Yes, by clever choice of psi. Agreed? By clever choice of psi. You can choose psi such that, okay, the expectation value of x is 0 and the expectation value of momentum is 0. Okay, I mean, you can make the average values of x and p go to 0 by clever choice of psi. Okay, so psi is in our hand. So what type of psi we choose, it's in our hand. Okay, so this is what we have done. Now, if somehow we can prove this term, so if somehow we can prove this particular term as h cross square by 4, okay, so if we can prove this term as yeah, so this is actually expectation of value of p square, and yeah, correct. So if we can choose this as h cross square divided by 4, then what do we get? Okay, I'm writing it here, the space is less. So what will happen is that, what will be this value? This value will be equal to del p square, so uncertainty in p whole square. So what will be the second value? The second value will be uncertainty in x whole square. So you can see it from here, and this will be greater than equals to h cross square by 4. Agreed? Then you can easily get del x del p as greater than equals to h cross by 2. So in this way we can get our uncertainty product, the most general uncertainty product. But we are left with one thing. We have to find this function, and this function can be found from here, and then we will prove that this function has a value equals to h cross square by 4. Okay, so if we successfully do that, then you can see uncertainty principle is already explained. Okay, so what is our target? Our next target is going from here to here. Agreed? So I hope you note it down. I'm going to rub everything that's there on the board. Okay, so just note down the Swatch inequality and note down these last steps that we are going to do. So these are the last steps that we'll do at the end. Okay, so what are our assumptions? Okay, remember that you need to choose such a psi, such a wave function psi, such that the expectation of value of x is 0. So what do you mean by expectation value of x? The position where you have maximum, the position where you can expect most of the electrons are coming. So you can choose that position to be 0. It's in your choice. And the expectation value of momentum to be 0. Okay. If this is done, then you remember the Heisenberg uncertainty principle in form standard deviation. So the uncertainty in x square will become what? Was actually the expectation value of x square minus square of expectation value of x. Okay, so the second term will vanish and you'll be left with the fact that the uncertainty in x square is equals to the expectation value of x square. Okay, that's why we have taken this particular assumption, because it makes our calculation very easy at the end of the day. Agreed? Now just assume this wave function. Just assume this wave function, and now we'll solve this wave function. Let us see what do we get. So in the next step, what will happen is you just do different integration by parts. Agreed? So what you need to do, you need to do integration by parts. So what will happen? So just IH cross as it is. So what is first term? So if you consider this as the first term and this as the second term, then integration by parts will tell you first term into integration of second term. So when you do integration of second term, the derivative will go and you will be left with x psi. Agreed? Okay. Now the limit will go from where to where? The limit will go from minus infinity to infinity. Agreed? Minus. So we are just using simple integration by parts that you have studied in your +2. Okay. So minus, so integration from minus infinity to plus infinity. So what is the integration by part second term? You have to do d by dx of first term. So you will get what? D by dx of first term. So my first term is actually psi star. Okay. So you'll do d by dx of first term into, remember, then there will be an integration of second term. So if you do integration of second term, what will you get? You'll get only x psi. Agreed on that part? Okay. So this whole thing into dx. Now you see that the wave function, this part will go to 0. So this part will go to 0. Why this part will go to 0? The reason is that at minus infinity and infinity, if you look at psi star psi, what is psi star psi? Psi star psi is probability. So this probability will go to 0 when your x goes to either minus infinity or plus infinity, because you don't expect any electron to reach at the infinite positions. For example, even if you do diffraction experiment, okay, since we are good at diffraction, so remember what was diffraction is, you take a slit and you have a screen. So how small can you make this slit so that you can get electron at minus infinity? It's not possible. Okay, so best thing is to assume that there is no electron reaching this part. Okay, because you cannot make this d so small that you can get an electron here. So it's better to assume that no electron reaches here. So probability of finding the electrons at the minus infinity and plus infinity is 0. Okay. So when the first term goes to 0, what are we left with? We are left with only the second term. So let me write down the second term. So we are left with only minus. Okay, remember this IH cross? This IH cross was there the whole time. Okay, the IH cross were there the whole time. So we are left with minus I H cross. Then the second term is integration from minus infinity to infinity. Okay, just write the second term. So you get this. So what is the conclusion? So the conclusion is that this is equal to this. So let me write it somewhere around here. Okay, so the conclusion is, so this is what we get. Now, so little bit one more step. So can I do differentiation by part for this term? This term is actually which one? This term. See what we are doing. We have just considered a term. We did goddamn integration by part, and now all we are doing is a differentiation by part. It's look big, but it's so easy. Okay, so when you do differentiation by part, I know how you do differentiation by part. So you'll get h cross I h cross. So what will be the first term? So this one you have to do differentiation by part for this. So the first term will be psi star. Okay, that term will remain as it is. Okay, so derivative will act on, say, the second term. Okay, d by dx, and then there will be an x as it is, and there will be dx. Okay, this is the first term. After that, what will be the second term for after the differentiation by parts? So integration, you'll get psi star psi. You'll get what? Psi star psi. It's very easy to do. Okay, it's not that difficult. So where are the limits? From minus infinity to infinity. Now, can you tell me what is the value of this integration? The value of this is 1. This is what? This is the total probability. You have studied this again and again in this lecture series. This is nothing but probability. So this is 1. So what you are left with? You are left with this. Now we'll do something. That something is, you will take this part and this part, put them on one side, and take IH cross and put it on the other side. So let me do. So what we have done is, we have taken this part and this part on one side, and we have kept this part on the other. So this is what we get. Okay, this is what we get. But wait, we are not done yet. A little bit of more derivation is left, because we have to reach there. Remember where we have to reach? Okay, now an interesting thing is, you see the right hand side of this equation. Okay, the right hand side of this equation is purely imaginary. Okay, because you have a I H cross, as a result of which you have the right to take only the imaginary part of this equation. Okay, so when you consider the imaginary part of that equation, you get, there will be 2I. Okay, I'm not going to explain this. This is simple complex mechanics. Okay, the imaginary part of, okay, the imaginary part of, so imaginary part of which term? Imaginary part of this term. So we have an integration I H cross. Okay, you have a d psi star by dx. You have a d psi star by dx into x into psi into dx. So this imaginary part is actually equal to minus I H cross. Okay, so somehow the real part has to be 0. So now what you do? Now we can just simplify this a bit. To simplify it, just square both sides. So if you square both sides, what you will get? You'll get a 4 multiplied with, okay, so 4 into, there will be a mod of imaginary part of this integral. So since we have squared both sides, there will be a square here, and this side what you will get? You'll only get h cross square. Okay, this is very easy to see. Now So can you just tell me one thing, that if I take the real part, so if I take the real part of this, so modulus of real part of this, sorry, the modulus of the entire function, I'm not considering real part. So if I do the modulus of this entire function, then of course the modulus of this entire function will be greater than the modulus of the imaginary part. Agree? This is normal complex mechanics. So what I'm trying to say is, if I take the modulus of this function, so what is this function? This function is some integration. So what I'll so yeah, some integration of IH cross d psi star, okay, divided by dx into x psi. So if I take this entire function, okay, and if I do a modulus of this function, then of course the modulus of this function will have a value which will be greater than, the imaginary part of the same function. So this is the function. So imaginary part of this will be of course less than the original function. Okay, so there won't be any 2 here. Agreed on this part? So in the next step, what I can write? In the next step, I can just write that my integration of I h cross. Okay, so what was my function? D psi star by dx into x psi. Okay, and there will be dx. So of course this function is greater than equals to h cross square by 4. And remember, we started explaining you from this function, and we used Swatch inequality in the very first of the derivation. Okay, so if you go to the initial derivation, then you will find that we have done from here. Okay, so I'm not going to derive it. And at the end of the day, what do we find? We find that uncertainty in P and uncertainty in X, when they are multiplied, they are it is greater than h cross divided by 2. Okay, at this, in the beginning of the lecture, so I stated it very carefully. I stated very carefully that somehow we need to reach this function from the initial starting function, and finally we reached. And then what we did, then we reached from here to here using the Swatch inequality. Okay, so that part has been done in the starting of the lecture. So this is the concrete proof of Heisenberg uncertainty principle. So it looks big, but it is actually small. We started with a particular function. First we did integration by part, second we did differentiation by part, sum equals to we did, and then at the end we use Schwarz inequality and we get Heisenberg uncertainty principle untempered. This is a real Heisenberg uncertainty principle. So the amazing thing is, this equation here, they automatically have the information of the uncertainty principle encoded in them by birth. Okay, so I hope you enjoyed this lecture. It was complicated, I know, but there is no other way, because many of the things are really complicated, so can't be simplified. So if you do this derivation again, if you look at this derivation again, things will be simple for you. Okay, thank you for listening. Bye bye. We continue our lecture series further in this course.